And first, I would like to introduce the working principle. What is an electrochromic device? So the working principle is similar to an lithium-ion battery. The difference is that we use the transparent conductor oxides to use as the electrodes, not metals. So when it deposits two electrochromic layers on each side and laminate with an electrolyte in between. When you apply the voltage that ions are shuttered between these two electrodes, then we can change the color of the devices. As you can see from the right figure, that it's a real window that uses electrochromic materials. As you can see, it can not only change the optical transmittance for the visible light and also for the real infrared. So that means we can not only control our lighting inside of the windows or the buildings, and also we are going to modulate the heat gain or the temperature inside of the building. So normally, basically speaking, for the electromaterials, it has big potential in the energy efficient buildings. For the EC materials, it can be classified as into two categories. First one is organic electrochromic materials. The second one is inorganic. They both have the advantages and the disadvantages. For example, for the organic electrochromic materials, it has a rich color appearance, but the bad thing is the stability is very poor. So once the sunlight shines on it, it will degrade very fast. The good thing for inorganic materials is it's much more stable than the inorganic materials. The bad thing is it can normally only has one or two color appearance, which is different from the organic electrochromic materials. As you can see, for the inorganic materials, so normally we have like transition metal oxide. As I mentioned from the this figure, that we have two electrochromic layers, which is compatible with each other. So we call one layer is the cathodic layers. The other one is called anode layers. So for the cathode layers, we normally use the tungsten oxide, and the anode layer we use the nickel oxide. So we combine these two layers and electrolyte in between with two TCO, then we have the full device. For the applications, in fact, for electrochromic materials is pretty broad. So normally in the market, we can see it's a rear view mirrors. We can block the strong light of the car from the behind. And also it can be used in a flexible display and for the goggles. This is very popular in Sweden, in fact. And also in the military purpose, we use this kind of things to change the color, not only from the visible light, but also for the infrared, for the comfort. And the biggest potential, as I just mentioned, that is for the energy efficient buildings to reduce the energy consumption inside of the modern buildings, especially in big cities. And this part, last part in the right figure here, so right now it has been applied to the fashion elements, for example, in mobile phones. So this is right now there's two companies in China trying to apply this kind of electrochromic materials in their real mobile phones. For example, for the back cover, you can, for the only one cell phone, it can change the color from different color appearance, which is pretty attractive for young generations. And also, for some devices, they can use electrochromic to block the camera, right? So when you want to use the camera, it can be appeared. So normally, it's just blocked by the electrochromic layer behind. Okay, so now I want just to briefly talk about the electrochromic history. So in fact, this phenomenon was found like 50 years ago, and in tungsten oxide, when it integrated with acid, so they can change the color from a transparent to the blue. Then this technology or this phenomenon was developed to use into the display industry. But at that time, as you know, in 1970s, liquid crystals was developed very fast, and it has the advantage of the fast response time. So, but for the electrochromic devices, normally the response time is not good as these liquid crystals. So, in the display industry, electrochromic technology doesn't stand up. So, and the scientists then initialize the concept for the smart windows. So, that which doesn't need very fast transition time. In 1999, a real wall was installed by the electrochromic layer windows. As you can see from here, that's a bank from Germany. They use the electrochromic windows. And also in 2005, some car, for example, the Ferrari Super American car from Italy, is also decorated with electrochromic windows. So in our real life right now, I think the most common electrochromic products can be observed is in the aircraft. For example, here, if we take the aircraft of Boeing 787, we will see that the window is used by the electrochromic windows. So you just need to change the color or change the transmitting or color state by pressing the button here. As I mentioned, in 2020, that's last year, two companies in China initialized the concept to use electromaterials in the mobile phones, as you can see from here. Okay, so like 5 years ago, a group in China that modulated that if big cities in China use electrochromic windows, how much energy we can save. So they simulated like three biggest cities from the north to the south part. So the energy saves can be like 10% in Harbin, and 15% in Shanghai, and 13% in Guangzhou. If we compare the primary energy consumption in China, I mean, this number will be very huge. Basically speaking, I mean, the potential for the electrochromic windows is very good. I mean, should be developed into the market. There are also some figure of merit for electrochromic devices. I listed here as the four most important part. The first part is called the optical contrast. For example, we want these devices can change the optical transmittance as much as it can. For example, from 100% to 0%, from a totally transparent state to a totally dark state. That will be very ideal. The second part is the response time. As I mentioned, the response time is not as good as a liquid crystal. But if for example, in window applications, a few minutes should be okay and acceptable. The third part is the color efficiency. That stands for how much energy consumed to change the color for the window. So basically speaking, we want to consume as less as energy for the devices. The last part is the cycling stability, which is a very, very important figure of merit for electrochromic windows. For example, not only electrochromic windows, but for any electrochromic-based devices, right? So once the devices is served, we want to use it as long as possible. For example, like 5 years, 10 years, or even 20 years, right? So this parameter is very, very important. And we have done some work related to the cycling stability, and I'm going to introduce it into the next slides. Basically speaking, as I just mentioned, the most widely studied material for electrochromic is the tungsten oxide. So tungsten oxide, from as prepared state, is transparent. For example, it's as transparent like here. If we insert charge into the film, it will get dark to form the compound like metal tungsten oxide base. So when we go to a reverse scan, the charge will be extracted, for example, like this. So it will become transparent again. The ideal case that the insert charge and the extract charge should be equal. That will be very good. The clone baking efficiency will be 100%. But in real cases, it's not. Normally, the clone baking efficiency is less than 100%. And also the inserted charge is normally a little bit larger than the charge that can be extracted, which means some ions are left inside of the electrode, cannot be extracted anymore. So after many cycles, this kind of a device will get degraded, will lose its electrochromic properties. Okay, here I will show you an example. As I just mentioned, this is the first curve of a CV curve of tungsten oxide in the range of 2.0 to 4.0 volts. And as you can see, at the very beginning, it's at the bleach state, which has an optical transmittance like 100%. when we insert charge into this film, as you can see, the optical modulation can reach to like 50%. So after 400 cycles, as you can see, the CV curves shrink a lot, which means the device lose part of its performance. As we can see it from here, as you can see right now, the optical modulation is only from 100% to 70%, like 20% of optical modulation is lost. That applies to the full visible light range. As you can see, we take the spectrum from 400 nanometers to 800 nanometers. After 400 cycles of series cycles, we see the optical modulation degrading. So we are seeking that probably because the ions are get trapped inside of the film. If our hypothesis is right, is that possible? We can detrap these trapped ions. So we applied an opposite current to the device, and after like 20 hours detrapping process, we try to recycle the film again. And you can see from the blue curves and the red curves, they are overlapped very well, which means the trapped ions are get detrapped from the films. And again, we compare the optical modulation, and you can see right now is that it retained to its initial performance. It can change the color optical transmission from 100% to 50% again. So that means our device can be get refreshed. So another question is that possible we can refresh the film many times, like multiple times. Every time we find the device get degraded, we can refresh to get the initial performance. The answer is yes, as you can see here. So for example, we cycle the film like 500 times and it gets degraded from the charge capacity curve. And also we observe the optical modulation is also get degrading, right? So then we can use the detrapping process to regain its initial performance. But as here you can see during the detrapping process, the bleach state is always kept the same. It's not, we cannot see any difference when we use our eye. And when we recycle the film, we see the performance is regained, right? So from the curve, you can see we can regain the initial performance as many times. So every time we find our device is lose its initial performance, we can use this kind of method to regain its initial performance. That's be very important for real applications. Okay, so next question will be asked that are these trapped ions in the electrode stable or not? So if we leave the system for a long time, are these trapped ions coming out from the film? So we did this as a following experiment. As you can see, initially we cycle the film to get degraded state and leave the system there without doing anything for 20 hours. So in principle, if the ions are coming out from the film, if we continue cycle, the initial capacity should be somewhere from here, right? But in fact, it's not. It's continues the initial degrading trend. It follows the same trend right here. So that means the trapped ions are stable inside of the film. If we do not apply the external stimuli, it cannot be extracted out. So like after we cycle it for twice, first 500 cycles and continue to do another 500 cycles. We want to check if is that possible we can regain its initial performance. The answer is yes. Yes, so we can extract to regain the refresh the film. And the next question will be asked how much time or how long we should apply this kind of current to refresh our films. As you can see here, we normally get is like 20 hours detrapping, which is pretty long, almost 1 day and 1 night. So we use multiple times, like it applies the current for 1 hour, 2 hour, and 4 hour separately. And we can check that almost like 7 hours, the films can regain its initial performance, right? So that means we can extract the ions a little by multiple times. Do not need to apply the time for like 20 hours, which is too long. Okay. So the next question we want to talk about is that if we extend the potential window from 2.0 to 4.0 to 1.50 to 0.0. But what happens? So the result is look like this. The Seebeck curves doesn't change too much, but as you can see here, so only after like 20 cycles, the films almost lose its charge capacity, right? The reversible charge capacity is almost losing. From the right figure, you can see here, this is how much charge are trapped during each cycle. And almost like after 20 cycles, the films, the charge can be trapped as it's very little, but the film reversible charge is also degrading very fast, right? The big difference from the purest result is that, as you can see, during the 2.0 to 4.3, this range only cycling the film. During the detrapping process, the optical modulation doesn't change, and also during the degradation period, only the color state is degraded, right? But this is different when we cycle the film in the range of 1.45 to 4 volts. Not only the color state of the film, but also the bleach state is degraded. That means in the two different range, we have two different kinds of traps inside the film. We call the traps which degraded the bleach state, only the color state, as a shallow trap. We denote the trap that not only degrades in the color state, but also the bleach state as a deep trap. So there are two different kinds of traps. The next question we want to know is that possible we can extract the charge or the ions from the deep trap? We apply the similar procedure, a constant current, and we observe that the optical transmittance of the films gradually return to its initial state, which means we are able to extract the ions from the deep trap as well. This is similar to the shallow traps. We can refresh the film, the initial performance of the film. Okay, we also want to know, are these trapped ions in the deep trap, they are stable or not? So we did the same cycling for 20 cycles to yield serious eye trapping effect and leave the system for like 20 hours without doing anything. So if optical transmittance doesn't change during this period, that means ions should stable inside the film. They are not coming out. So the result we show here is proved our hypothesis that the ions inside of the deep trap, they are also stable. Okay. And here I want to show that once the potential window, we lower the potential limit from 2.0 to like 1.7 or 1.5. Every time after cycling and after the detrapping process, we notice there is a small portion of the optical transmittance cannot refresh or cannot regain its initial value. That means there is another kind of trap, which since this optical transmittance cannot be go back to its initial performance, we call this kind of trap as a irreversible trap. Okay, but the good thing is that this portion is very small, so we can almost neglect it in the real applications. And also, next question we want to consider the real applications is that how much lithium ions or how much charge we should insert it into the electrode to yield less eye trapping effect. And here, by compare the different potential window, notice that when the X value is less than 0.65, the film shows much stable state, right? So here is the value. As you can see, for real devices, we should keep this value below 0.65, so that the device will be normally, I would say, it's stable. Okay, for the detrapping process, I just mentioned it's we applied a constant current. So if we change the constant current to the constant voltage, what happens next? As you can see here, we cycle the film in the range of 1.5 to 4.0, this range, to get color state degraded and the bleach state degraded. So we applied constant voltage, for example, 5.5 volts for like 20 hours. We observe there is a sharp optical transmittance increase. when the voltage applied for like 2 hours, from here to here is like 2 hours. At the same time, we observe there is a current density peak, which is very, very interesting phenomenon. I mean, this peak doesn't appear at the very beginning of the potential application, but after a while, that means this system have to overcome the energy barrier, so that the ions from the deep trap can be released. I mean, currently the physics from the behind is not clear yet, but I mean this phenomenon is very interesting. Okay, we compare the constant potential detrapping process for the shallow traps and the deep traps. For example, for the shallow traps, it's the red curve. For the deep trap, it's the blue curve. As you can see for the blue curve, we can observe there's a current peak here, which indicates the release of the ions from the deep trap. And also, we studied how much voltage should be applied to the system in order to release these ions from the deep trap and the shallow traps. So here is the answer. So when the system, when the applied voltage is less than 5.25 volts, for example, 5 volts, 4.5 volts, we didn't observe the sharp increase of the optical transmittance, which means ions are not extracted from the deep trap, right? So when we apply the potential is over 5.25, we observe the sharp optical increase, and the high applied voltage, the earlier these ions are get released. This is pretty interesting. Okay, as you can see from here. So that's from the we talked a lot about the eye trapping, detrapping. People may ask, do you have a direct evidence to support your hypothesis that there's eye trapping, detrapping? Okay, so here is the answer. So for example, we have a tungsten oxide we immersed into electrolyte at the very beginning. So in principle, we didn't do any experiment yet. So at this state, like state 1, in principle, it should be there is no lithium inside of the film, right? So when we cycle like 20 times to yield serious eye trapping phenomena, so at this state, like state 2, there should be a lot of lithium ions inside of the film, right? So then we apply the constant current or constant potential to refresh the film, and you can see we are able to refresh the film, and yet the state 3. So in principle, the state 1 and the state 3, there shouldn't have any lithium ions inside, but the state 2, there should have a lot of lithium ions, right? As you can see here, we observed like 20% of the lithium ions as the state 2, and like almost 0% of the lithium ions inside of the state 1 and state 3, which I mean give our direct evidence that the degradation of our electrochromic films is because of the eye trapping, and we are able to detrap these ions from the traps to yield the state 3, which doesn't have lithium ions anymore. So this experiment gives our very good support, showing that the degradation of electrochromic materials is because of the eye trapping, and we are able to refresh the devices. Okay, so let me summarize here about my talk. Very important that we found 3 different traps inside of the tungsten oxide. For example, the first we call it like shallow traps. It's only degrading in the color state, but the bleach state are almost keeps the same. The second is called deep traps. The deep traps is different from the color traps, that it's not only degrading in the color state, but also the bleach state as well. And also we found the third trap we called irreversible trap. As you can see here, so after detrapping, we are not able to regain the initial performance at the short wavelengths here. So we call this trap as a deep trap. The good thing is, I mean, it's only very small portion. Doesn't affect the real applications. This is for the tungsten oxide. In fact, we also found in the titanium dioxide electrochromic materials, shallow traps are also being observed, which means it's similar to the tungsten case. here. It's only degrading the color state, but the belief state are always kept the same. All right, I think that will be all for my talk today. The next step, we are going to develop the full solid state electrochromic devices in our life. Okay, so thank you very much.